So in the last video, we've seen how we reduced from 81 constants to 36 constants in order to make our study more comprehensive and easy. Now we'll have a look at a few of the material properties and material symmetries, and then proceed to deduce the relations again. So the first kind of materials, in this we would be analyzing what different materials actually mean, and we'll try to also reduce the matrices to a certain extent in this section. So when I talk about a monoclinic material says that whenever I measure a property of a particular material, of a monoclinic material, it differs in three different directions, but there is one plane of symmetry. Now when I talk about one plane of symmetry, it states that, let's say the object basically has three planes. So this is a plane and this is another plane. When I say one plane of symmetry, if I take a set of coordinates in this plane, and if I refer them with respect to this plane, they would be the mirror images of each other. That means all the points in the first plane are symmetric about the second plane. So for which I can develop my stress strain relation for the first plane. Let's say the first plane is 1, 2, 3. The stress in the first plane 1, 2, 3 is the matrix, the stiffness matrix times the strain 1, 2, 3. Similarly, stress strain relation for the second plane, that is 1 dash, 2 dash and 3 dash, the stress 1 dash, 2 dash, 3 dash in that plane would be the stiffness matrix times the strain 1 dash, 2 dash, 3 dash. But here what we need to observe is that we're using the same stiffness matrix, right? So hence we can uh, uh, actually deduce the stiffness matrix into the following. Okay, there's another elaborate study behind this, but since I'm just giving you the summary, the stiffness matrix is deduced into this region wherein C14, C15, C24, C25, C34, 35, and these terms C46, C56 are made to be 0, and the lower triangular matrix is the same as the corresponding elements, like C21 would be nothing but C12. Okay, so this is for monoclinic material. Now when I talk about orthotropic material is a kind of material in which the material properties change with respect to perpendicular axes. Okay, so in short, the definition here says the mechanical properties vary along three mutually perpendicular axes. So from that, they've reduced the matrix into this form. That is, originally we had a 6 by 6 matrix with so many elements. For monoclinic elements, for monoclinic material, we've got these terms to 0. In here, we've got these terms, that is C14, C15, C16 to 0. What you need to observe is a 3 by 3 matrix on the top is 0, and this triangular matrix in here is also 0. So you basically have 9 constants in here, 9 independent constants in here, that is 1, 2, 3, 4, 5, 6 and 8, 9. Now in orthotropic, we've got two cases when I talk about specially orthotropic and generally orthotropic. And when I talk about specially orthotropic material, see, we know that the properties in an orthotropic material change with respect to perpendicular axis. Now it might not be necessary that I take the perpendicular axis like just how the planes are in terms of x, y and z. Okay, I might be taking the same axis as a reference, or I might be taking a different axis as a reference. So if I take the same axis as that of the planes given, like if I take my first axis in this manner as an x, second axis in manner of y, and third axis in manner of z, I would be considering that material as a specially orthotropic material. Okay, but let's say the actual axes are somewhat like this for this material, and you see, and I take my x-axis slightly different from the object's coordinate axis. Similarly, I take my y-axis different from the object's coordinate axis, and z different from the object's coordinate axis. So if I continue my study in this manner, we call it a generally orthotropic material. Now, similarly, for a transversely isotropic material and an isotropic material, we've got these two relationships of the stiffness matrix. As I already told you in the previous video what an isotropic material means. Here this is that it has infinite planes of symmetry. That is, wherever and whichever direction you observe, the material properties wouldn't change. Okay. When I talk about a transversely isotropic material, like there's only one plane in which the material property is the same. That it might be 1 2 or 2 3 or anything. So there's only one plane in which the property is the same. So in summary, if I have to dilute the relationships, for an anisotropic material, we've got 21 independent constants. For a monoclinic material, we've got 13 independent constants. For a specially orthotropic, we've got 9 independent constants. For a transversely isotropic, we've got 5, and for isotropic, we've got 2. See, when I am saying about isotropic, we're just using between C12 and C11. We're just oscillating between these two values, and hence we've told that there are only 2 independent constants. Now, I would be telling about the plane stress assumption in the next video, but this is all for now.